Hello friends, welcome back to my YouTube channel. Today will be the 40th part of my discussion on distillation, and I'll be talking about one more method that is used to find the number of ideal stages in a fractionating column. The method is Lewis-Sorel method. Till now I have discussed two methods for finding the number of ideal stages. The first one was the McCabe method, and the second one was the Pongent separate method. And today I'll be talking about the Lewis-Sorel method. Basically, in this video, we are going to understand the method. We are going to know what are the steps involved in the method for finding out the number of ideal stages, or you can say number of theoretical stages, or the number of equilibrium stages in a typical tray column or in a typical fractionating column. So let us begin the discussion. Okay, to begin with, let us know the basic information regarding the Lewis-Sorel method. So the Lewis-Sorel method, it is used to find the number of ideal or theoretical or equilibrium stages that are required to bring about the desired separation by fractionation in a tray column. So the method will give us the number of ideal stages, or you can say the number of theoretical stages or equilibrium stages that are required to bring about the desired separation by fractionation in a typical tray column. The method, that is the Lewis-Sorel method, it is based on entirely the material balance. The method is entirely based on the material balance. That means energy balance is not involved in this particular method. To be more specific, the method uses equations of the operating lines for rectifying and stripping sections. So the method uses only these equations. Which are these equations? The equations for the operating lines for the rectifying and stripping sections. Along with the operating line equations, the method also uses the distribution diagram, or if an equilibrium relationship is available, then that equilibrium relationship may be used. Either the distribution diagram or the equilibrium relationship, any one of these two can be used in this method. You know the distribution diagram, this is plot of equilibrium concentrations of the more volatile component in vapor and liquid phases. The mole fraction of the more volatile component in the liquid phase, it is plotted on the x-axis, whereas the mole fraction of the more volatile component in the vapor phase, it is plotted on the y-axis. And when you plot these two quantities, you get a curve that is called the equilibrium curve or the distribution curve, and this diagram is called the distribution diagram. In this case, or in our discussion, we are going to consider a system of two components. Which are these two components? A and B. And out of these two components, A is the more volatile component. That means A has a lower boiling point and a higher vapor pressure if you compare with B. And X and Y, these are mole fractions of A, which is the more volatile component, mole fraction of A in liquid and vapor phases respectively. And when the two phases are in equilibrium with each other, when the vapor and liquid phases, they are in equilibrium with each other. So we are plotting mole fractions of A in the liquid and vapor phases against each other when the two phases, when liquid and vapor phases, they are in equilibrium with each other. That means every point on this curve, it represents an equilibrium point. So if you choose any point on the curve, the coordinates of this point, for example, the x coordinate of this point, let us say x star, and the y coordinate of this point, let us say y star. So in this case, X star and Y star, they are in equilibrium with each other. In short, in simple words, this is a plot of equilibrium concentrations. So you can either use the distribution diagram. For that, you need to know the XY data, which we called the equilibrium data, VLE data, vapor liquid equilibrium data, that is various values of X and corresponding values of Y that are in equilibrium with the values of X. So you can plot that data to get this curve. So if this data is not known to you, and instead of that, an equilibrium relationship like this one is known. That means if you know the relative volatility, in this case alpha AB is the volatility of A relative to B. So if alpha AB is known to you, you can get this equation. So on the left hand side, on the right hand side of the equation, you'll have X, whereas on the left hand side, you'll have Y. So that means after putting the value of alpha AB, you'll be getting an equation which is a function of X. So an equilibrium relationship like this, if it is available, then there is no need of plotting the distribution diagram. You can directly use the equilibrium relationship while applying the method. You'll shortly know how this is done. For time being, what you have to remember, along with the operating line equations for operating lines of rectifying and stripping section, along with these two equations, we also need either the distribution diagram or an equilibrium relationship. So you'll come to know as we proceed on our discussion. Let us first look at a typical tray column. I have shown this, or I have used this in all of my discussions on tray columns. Let me briefly describe this to you once again. So you have a typical cylindrical vessel in which you have trays. This dashed lines, they represent trays. I am numbering the trays. The topmost tray is the first tray or first plate, you can say, because in a plate column or tray column, plate or the tray, it is acting as a stage. So topmost stage, I am calling it to be the first stage, and the last stage in the column, I am calling it to be nth plate, capital nth plate. Then the feed solution, it will be admitted on one of the tray that is almost located centrally. We call that plate as the feed plate. So feed is entering at a molar flow rate of F. It has a mole fraction of XF, mole fraction of the more volatile component in it, and HF is the molar enthalpy for the feed. So feed is admitted on the feed plate, or the plate on which feed is admitted, we call that plate as the feed plate. Then the other trays, this is nth plate, which is in the rectifying section. You know what is the rectifying section, and there are two stages or two plates that I am showing in the stripping section. One is nth plate and the other one is m plus 1th plate. So after entering the column, the feed, liquid part of the feed is going to go down. So there are different types of feeds. Actually, there are 5 different types of feeds. I have made a separate video on different types of feeds to a typical tray column. The type depends on the thermal condition of the feed. So whatever may be the feed, the liquid part of it is going to come down, and then it will be taken to the reboiler, where it will be heated to create the vapor phase. The vapor phase will be admitted into the column. Then the vapor phase will be rising through the column. It will be taken out. At the top, it will be sent to a condenser, where heat will be removed to get a condensate, and then the condensate will be divided into 2 parts. One will be written back to the column as the reflux, whereas the other part will be taken out as the top product, or we call that as the distillate. So distillate will be removed. Distillate of the top product, it will be removed at the molar flow rate of D, which will have the mole fraction of A that is mole fraction of more volatile component in it, XD, and enthalpy, molar enthalpy of the distillate is HT. Then the reflux stream that is going back to the column, it will be admitted at the molar flow rate of L0 or yellow, and the composition, mole fraction of the more volatile component in the reflux will also be XD. Even the enthalpy of the reflux will be same as that of the distillate, because after condensing there is simply division of the stream. There is no any composition change involved. So reflux, after entering the column, it will be flowing down and it will join the liquid part on the feed plate, and then from the bottom you are removing the bottom product, or you also call that as residue. It will be removed at the molar flow rate of W. It will have the mole fraction of more volatile component XW in it, and molar enthalpy for the bottom product will be HW. So this is a typical tray column, and the schematic tells you how it operates. Now let us know about this rectifying section. You know, the rectifying section is the section of the column above the feed plate, the one that is shown with the help of this envelope. So for the rectifying section, the equation of the operating line, I have derived it. I have a separate video on operating line for the rectifying section. I am giving link to that video in the description section. Let me take the equation directly in my discussion in this video. The equation is yn plus 1 is equal to r upon r plus 1 into xn plus xd upon r plus 1. So xd, r will be known to us, and xd will be known to us. So if you use those two values, you are going to get an equation of this form. What is that equation? Yn plus 1 is some function of xn. That means here in this case, xn is the mole fraction of the more volatile component in the liquid that is leaving nth plate. So xn will be associated with this stream, whereas yn plus 1 is the mole fraction of the more volatile component in the vapor phase that is coming to nth plate. And the stream that is coming to nth plate, it is coming from n plus 1 plate. So yn plus 1 will be associated with this stream. So the equation of the operating line gives a relationship between the vapor that is coming to a plate and the liquid that is leaving the plate. So that's why after putting the value of r and xd, which will be known to us, you are going to get an equation of this form. Yn plus 1 is equal to f of xn. And the Lewis-Sorel method makes use of this equation in its application. You'll shortly understand this. I hope this is clear to you. If you have any doubts, you please let me know. You please mention them in the comment section. Let me first erase this so that I can proceed with the remaining discussion. In this case, R is the reflux ratio, XD is the mole fraction of A in the distillate. And what is A? The more volatile component. R, the reflux ratio, is ratio of the reflux stream to the distillate stream. That is ratio of molar flow rate of the reflux, L0, to the molar flow rate of the distillate, that is D. And in this case, L0 is, as I said, reflux molar flow rate, and D is distillate molar flow rate. And you must be remembering, while getting this equation, we have made an assumption of equimolar overflow, which is nothing but the liquid molar flow rate is same for all the plates. That is L0 is equal to L1, that is equal to L2, that is equal to Ln. So L1 represents the liquid molar flow rate that is leaving stage 1, liquid molar flow rate that is leaving stage 2, so on and so forth. And in general, Ln is liquid molar flow rate that is leaving nth plate. So this is one of the simplifying assumptions of the Markov-Thiele method, and we are going to use the same in the Lewis-Sorel method as well. Now let us look at the stripping section. This, as you know, the stripping section is the section of the column below the feed plate. So this is the stripping section. And the equation for the operating line for stripping section, the equation is ym plus 1 is equal to L bar m divided by L bar m minus w into xm minus w upon L bar m minus w into xw. That means if you use the value of L bar m and w, you are going to get an equation for ym plus 1 in terms of xm. And the method uses this form of equation for finding the number of ideal stages. Okay, so let us just understand the equation. So the equation, it is relating ym plus 1. Ym plus 1 is the mole fraction of the more volatile component in the stream that is leaving m plus 1th plate, vapor stream that is leaving m plus 1th plate. So ym plus 1 is associated with this. Whereas xm is the mole fraction of the more volatile component in the liquid stream that is leaving mth plate. So this is the liquid stream that is leaving mth plate. That means xm is associated with this. So ym plus 1, it is related to xm to the equation of the operating line for the stripping section. Again, L bar m, it represents the liquid flow rate that is leaving mth plate, the liquid molar flow rate that is leaving mth plate. So this is the liquid flow rate that we are talking about. Now this liquid flow rate will be different after you use the simplifying assumption of equimolar flow rate, where the liquid molar flow rate is same for all the trays, even in the stripping section. But you should know that it is different. The liquid flow rate in the stripping section is different from the liquid flow rate in the rectifying section, because due to the addition of feed, because when the liquid comes in the stripping section, it also has the liquid that comes along with the feed stream. In short, L bar, that is liquid flow rate in the rectifying section, is different from, let me write it. So L, that is liquid flow rate in the stripping section, liquid flow rate in the rectifying section, it is not equal to the liquid flow rate in the stripping section. Liquid flow rate in the rectifying section is not equal to the liquid flow rate in the stripping section. So that you must remember. So in order to indicate the difference, we are using a bar or this notation, or the notation L. Okay. So in short, you must have understood, after putting the values of L bar m, so L bar m, the value of L bar m will be decided by the type of the feed that is involved. And W is the molar flow rate of the bottom product, as you know. So L bar m, this is the molar flow rate of the liquid that is leaving m tray or m plate, I have told you. Then W is the molar flow rate of the bottom product, and XW is the mole fraction of A, that is the more volatile component in the bottom product. And of course, the simplifying assumption of equimolar overflow is also used in the stripping section. So I have made a separate video where I have derived the equation for operating line of the stripping section. I am giving link to that video in the description section. So here also you have the assumption of equimolar overflow is valid for the stripping section as well. That is L bar 1 is equal to L bar 2 is equal to L bar 3, that is equal to L bar M. That is liquid molar flow rate from tray number 1 in the stripping section is equal to liquid molar flow rate from tray number 2 in the stripping section, and in general we are going to denote that as L bar. I hope this is clear to you. If you have any doubts, you please let me know. So equation of the operating line for the stripping section, it is also used in the Lewis-Sorel method. And I have taken that equation directly. I have derived it in my earlier video on the operating line for the stripping section. You please watch that video. You'll understand everything behind this equation. Next, the method, that is Lewis-Sorel method, it can be applied in two ways. You can apply it either from top or bottom of the column. That means you can start from the first plate or you can start from the last plate. It can be applied in both the ways. So the method, it can be applied either from the top or bottom of the column. If it is applied from the bottom, you will have to start the calculations that are involved, they will start from the reboiler, and these calculations will end with the condenser. So if the method is applied from the bottom, so you are moving in this direction, so your calculation will start at the reboiler and they will end at the condenser. Whereas if the method is applied from top, that means if you are starting from the condenser, if the method is applied from the top, you are going to start from the condenser. The calculations will start from the condenser and they will end at the reboiler. So you are going to start at the condenser and the calculations, they will be ending at the reboiler. In this particular video, I am going to tell you how to apply the Lewis-Sorel method from top to bottom, where we will be starting from the condenser and then we will be stopping at the reboiler. So we will know what are the steps involved in applying the method in this way from top to bottom. So as I said, we are going to understand how to apply the method, the Lewis-Sorel method from top to the bottom. So method applied from the top. So for the rectifying section, we have the operating line. We just have written the equation yn plus 1 is equal to r upon r plus 1 into xn plus xd upon r plus 1. Now, if you are starting at the top and if you consider the first stage, which I am showing over here, this is the first stage or the first plate in the column, that is we are at the top. So you can just look at the diagram or the schematic diagram that I have shown. You have this vapor stream that is leaving the first plate. So mole fraction of the more volatile component in it will be Y1. The same vapor stream is coming out at the top. So it will have mole fraction of the more volatile component Y1 in it. And then the vapors, after going to the condenser, they will be condensed and you are going to get the distillate and the reflux. And the mole fraction of the more volatile component in the distillate is XD. So in the condenser, you are just changing the phase. Vapors are converted to liquid. The vapor phase is converted to the liquid phase. So there is no any composition change involved, which means that XD, that is mole fraction of the more volatile component in the distillate and also in the reflux, is same as that of Y1. Because the same vapors rising from the top, which have Y1 as the mole fraction of the more volatile component in them, the same vapors are condensed in the condenser. So that's why there is no any change in the composition. That means XD is equal to Y1. And we are going to show this with the help of this equation. So for the first stage, Xn is equal to XD and Yn plus 1 is equal to Y1. If you look carefully at this equation, on the left hand side of the equation, you have composition in the vapor phase in n plus 1th plate. Whereas on the right hand side, you have composition in the liquid stream, but the liquid stream is leaving the tray that is coming before n plus 1th tray, which is nth tray. So you have liquid phase composition on an earlier tray and vapor phase composition on a later tray. So taking this point into consideration, if you look at stage number 1, then the vapor phase leaving the stage number 1, if it has a composition of Y1, the tray that comes earlier to first stage is nothing but the condenser, in which the composition is XD. Composition of the liquid in the condenser is XD. That's why in this case, if Xn is XD, if the condenser is considered to be an earlier stage with liquid phase composition of XD, the latter stage, which is the first stage or first plate in this case, will have a vapor with composition Y1. So, if this equation is to be used for first stage, stage number 1, then these are the conditions. Xn is equal to XD and Yn plus 1 is equal to Y1. So, if you use these conditions, you are going to get this relationship. XD is equal to Y1. So, let us see that. So, therefore, if I use this information, Y1 is equal to R upon R plus 1 into XD. Yn plus 1 is replaced with Y1 and Xn is replaced with XD. So, you have Y1 is equal to R upon R plus 1 into XD plus XD upon R plus 1. So, that means you can take XD common. So, it will be R plus 1 upon R plus 1. So, therefore, Y1 is equal to XD is taken out as a common term. And in the bracket, you have R plus 1 upon R plus 1. So, R plus 1 gets cancelled and you are left with Y1 is equal to XT, which is again true. You can easily understand from what is happening at the top of the column. And same now we have proved with this mathematical equation. Y1 is equal to XT. So, with this understanding, that means the calculations for first stage will be completed when you know values of Y1 and X1. Because Y1 and X1, these will be, let me tell you. So, this is the first stage. Okay, I can show it on the diagram itself. So, you have the first stage. This is composition in the vapor that is leaving first stage, and X1 is the composition in the liquid that is leaving first stage. And since this is ideal stage, we are talking about ideal stages. So, this being an ideal stage, X1 and Y1, they will be in equilibrium with each other. They will be in equilibrium with each other. They will be in equilibrium with each other. That means the calculations for first stage or for our analysis for first stage will be completed when we know these values. So, at this point of time, we know the value of Y1. How? Because it is equal to XD and XD is provided to us. We will be knowing XD. Now, what is left? We need to know the value of X1. And for that, we are going to use, we have two options. We can either use the distribution diagram or you can use an equilibrium relationship if it is available. Equilibrium relationship will be formed if you know the relative volatility, because the equation that you can use, I have just told you. So, we will understand both the ways. Let me first erase this. Okay, so after getting Y1, we need to get X1, and for that we are going to use the distribution diagram. We will know how to use the distribution diagram, and then we will know how to use the equilibrium relationship. In actual application, you will do any one of these two. You will either use the distribution diagram or the equilibrium relationship, whichever is available to you. So, let me first erase it. So, The distribution diagram, as I said, this is plot of x versus y. Small x, the mole fraction of more volatile component in the liquid phase, plotted against y, the mole fraction of more volatile component in the vapor phase, equilibrium concentrations. And the diagonal line is drawn for reference, and the actual plot will be the equilibrium curve like this. So now here you know y1 because it is equal to xd, and xd is known to us. So we are going to take that value of y1 and come to the distribution diagram. We are going to locate y1 wherever it is, depending on its value. The only thing is it will be located on the y-axis. Then we are going to move to the equilibrium curve, and we are going to get the corresponding value of x1. So this point, which has coordinates of x1, y1, and this point being lying on the equilibrium curve, x1 and y1, they will be in equilibrium with each other. So this is how you can use the distribution diagram. If you have an equilibrium relationship like this, you can do this, or you can use the equilibrium relationship. Y1 is equal to alpha AB x1 divided by 1 plus alpha AB minus 1 into x1. So y1 is known to you, alpha AB is known to you, x1 is unknown, so you can get x1. So you have two choices depending on what is given to you. You can either use the distribution diagram, or you can use the equilibrium relationship. The idea is to get x1. So for first stage, you will be getting x1 and y1. That completes analysis, or you can say calculations for stage number 1. Now let us go to stage number 2. For second stage, we are going to use x1 that was obtained in the previous stage, either from the distribution diagram or the equilibrium relationship. So using x1 obtained in the previous step, we will use the equation for the operating line for the rectifying section. And if it is written for the second stage, it will be written like this. Y2 is equal to r upon r plus 1 into x1 plus xd upon r plus 1. So you are going to get y2 because r will be known to you, xd will be known to you, x1 is known in the previous step, so you can get y2. So take that value of y2, come to the distribution diagram, locate y2, go to the equilibrium curve and get the corresponding value of x2. Or if you know the equilibrium relationship, you can use the equilibrium relationship. Y2 is equal to alpha AB x2 divided by 1 plus alpha AB minus 1 into xt. The objective is to get the value of x2. So calculations for the second stage will be completed when you know the value of y2, and then by using the value of y2, you know the value of x2. So let me just write over here. So you are getting the value of y2, and then using the value of y2, you are going to get the value of x2. Then for the third stage, we are going to use the value of x2 that we get in the previous step. X2 that was obtained. So for second stage, we got value of y2, and then we got the value of x2. Now we are going to use the value of x2 in our calculations for the third stage. So using x2 that is obtained in the previous step, you get y3 by using the equation of the operating line. So y3 is equal to r upon r plus 1 into x2 plus xd upon r plus 1. So after getting y3, you are going to use it on the distribution diagram. So y3 is located, then the corresponding value of x2, which is in equilibrium with y3, corresponding value of x, which is in equilibrium with y3, that is x3, it is obtained. So in this way, you are going to get x3. Or if an equilibrium relationship is known to you, you can get it by using that equation. So y3 is equal to alpha AB x3 divided by 1 plus alpha AB minus 1 into x3. So you can get x3 either from the distribution diagram or from the equilibrium relationship. So that will give you x3. Then you are going to move to, so for the third stage, you have now got value of y3 and you have got value of x3. So in general, if you keep doing this and if you reach any stage, say kth stage, for kth stage, the equation will be written like this. And for writing that equation, we will need the value of x that was obtained in the previous step. That is, we will need the value of xk minus 1. So with that, you can write equation for yk. So yk will be r upon r plus 1 into xk minus 1 plus xd upon r plus 1. So xk minus 1 will be known to you from the previous step. R and xd, of course, they are known to you. That means you'll be able to get the value of yk, and then using the distribution diagram, you locate yk, go to the equilibrium curve and get the corresponding value of xk. So that means you are going to get xk, and if you have the equilibrium relationship, you can use it to get xk. Yk is equal to alpha ab xk divided by 1 plus alpha ab minus 1 into xk. So either ways, you are going to get the value of xk. So calculations for kth step will end after getting the values of yk and xk. So in this way, we have considered any stage, kth stage, I'm calling that as kth stage, and how the equation for the operating line is used for that stage I have told you. Okay, so after doing calculations for kth stage, you'll be following the steps that we have just understood till kth stage. You are going to follow those steps till this condition is satisfied. Xk is less than xf. Xk is less than xf. So if this happens, then you can declare that kth plate is the feed plate, because on the kth plate where you have calculated, or you have got the value of xk and you are checking that, or you are finding it to be less than xf. What is xf? The composition of the feed, the mole fraction of the more volatile component in the feed. So if xk becomes less than xf, you are going to declare that kth plate will be the feed plate, or kth plate is the feed plate. That means you are going to use the equation for the rectifying section line till xk becomes less than xf. I hope this is clear to you. So if this is happening for the kth plate, then kth plate will be declared as the feed plate, or kth plate is the feed plate. Therefore, you can say now if the kth plate is feed plate, then k minus plate, remaining k minus 1 plates will be in the rectifying section. So the number of plates in the rectifying section will be k minus 1, and kth plate is the feed plate. I hope this is clear to you. So in this way, all the stages in the rectifying sections are covered. So when you are going to say this, when xk becomes less than xf, it becomes less than xf. When your calculations for the rectifying section, they are completed. Now you know how many stages are in the rectifying section, and you also know what is the number of the feed plate. So if this is happening on kth plate, what is happening? Xk is becoming less than xf for the first time. So you are getting x1, x2, x3, and you have got xk which is less than xf. Then you are at the feed plate. So Next, you have to proceed, but for doing that, you will be using equation of the operating line for the stripping section. Because after crossing the feed plate, you'll be in the stripping section. So let me show you over here. So now you have, I'll just try to show. So you started with the first plate, second plate. Let us say this is the feed plate. And then kit plate is over here, where on the feed plate composition is XF, and on the kit plate the composition is XK, but XK is less than XF, which ensures that you are in the stripping section. So that's why the next plate will be in the stripping section, and therefore you'll have to use the equation of the operating line for the stripping section. I hope this is clear to you. So now for the stripping section, let us know what is to be done for the stripping section. So first thing is, we are going to use the equation of the operating line for the stripping section. What is that equation? Ym plus 1 is equal to L bar m divided by L bar m minus W into Xm minus W upon L bar m minus W into Xw. So now after kth plate, which is the feed plate in our discussion, now next plate will be K plus 1th plate or K plus 1 stage, which is in the stripping section. So this equation will be written. For that, we will be using the value of Xk, which was obtained in the previous step. So the equation now will be written as Yk plus 1 is equal to L bar m upon L bar m minus W into Xk minus W upon L bar m minus W into Xw. So this is going to give you Yk plus 1. So you are going to get Yk plus 1, and you are going to use Yk plus 1 to get Xk plus 1, which is in equilibrium with Yk plus 1. So you are going to look at Yk plus 1, you are going to go to the equilibrium curve, and then coming back to the x-axis, you are going to collect the value of Xk plus 1. So the calculations for the stage K plus 1 will be completed when you know Xk plus 1 and you also know Yk plus 1. First you will be knowing Yk plus 1 and then you will be knowing Xk plus 4. So either from the distribution diagram, or you can use the equilibrium relationship. Yk plus 1 is equal to alpha AB Xk plus 1 divided by 1 plus alpha AB minus 1 into Xk plus 1. Yk plus 1 is known and your objective is to get Xk plus 1. After that, then you'll be doing calculations for K plus 2 stage. And for that, you are going to use the equation of Yk plus 1, which was obtained in the previous step. So using the value of Yk plus 1, you are going to get the equation for Yk plus 1. Yk plus 1 will be equal to L bar m upon L bar m minus W into Xk plus 1 minus W upon L bar m minus W into Xw. So getting this value, after getting the value of Yk plus 1, you are going to get the value of Xk plus, after getting Yk plus 2, just let me write it neatly. So after getting value of Yk plus 2, you are going to go to the equilibrium curve, distribution diagram and find out the corresponding Xk plus 1. Or if you know the equilibrium relationship, you can use that to get Xk plus 1. So Yk plus 2 is equal to alpha AB into Xk plus 2 divided by 1 plus alpha AB minus 1 into Xk plus 2. Yk plus 2 is known, you can get Xk plus 2. So you have to use one of this. If distribution diagram is available, you use the distribution diagram, and if an equilibrium relationship like this is available, you can use that. So you are going to get Xk plus 2. So in general, if you go on doing this, K plus 1, K plus 2, K plus 3, in general, if you are doing it for K plus 2th stage, Then for that you will need to use previous equation of the value of y that was obtained in the previous step. And what is that equation? What is that value? Xk plus q minus 1. That means previous to qth stage, k plus q stage, it will be xk plus q minus 1 stage. So you are going to get xk plus q, that is equal to L bar m upon L bar m minus w into xk plus q minus 1 and minus w upon L bar m into w into xw. And now what you'll do after getting yk plus 1, you are going to use the distribution diagram and get the corresponding xk plus q. Or you can use the equilibrium relationship to get xk plus q. Yk plus q is equal to alpha ab xk plus q divided by 1 plus alpha ab minus 1 into xk plus q. So you can get the value of xk plus q. So you are going to follow these steps till xk plus q, it becomes less than xw. Xk plus q becomes less than xw for the first time. So you are getting lower values of, as you are proceeding, you are getting lower values for x, and a stage will be reached when you get that value of x which is less than xw. So that means you have arrived at the reboiler where the pump position is xw, and now your method will stop. You are going to stop because you have arrived at the bottom of the column. You started at the top and now you are at the bottom. You started at the condenser, now you are at the reboiler. So when xk plus q becomes less than xw, then you have reached the reboiler, as I said. Therefore, the number of plates in the stripping section are q, because k, out of this k, if you remember, stages, k minus 1 stages are in the rectifying section, kth stage is the feed stage, and remaining all stages are in the stripping section q. So out of this q minus 1 stages are in the stripping section, and there is one reboiler. So q minus 1 plus 1 is q. So the q minus 1 are the stages and 1 is the reboiler. Okay, so the number of plates in the stripping section are q, but q also includes the reboiler. Q also includes the reboiler because you have got this when x has become less than xw. So this q includes the reboiler. So at this point, your method will end and you will be knowing the number of ideal stages in the tray column. Okay, so total number of stages, how are you going to? The total number of stages are k plus 1, k plus q. This number includes the reboiler, that is Ni is equal to k plus q, and this Ni includes the reboiler. K plate is the feed plate. K minus 1 stages in the rectifying section and q minus 1 stages in the stripping section. So you are going to report Ni number of stages and you are going to say that this includes the reboiler. And you are going to report the K plate where X had become less than XF for the first time. And then you are at the reboiler when X becomes less than XW for the first time. So in this way, you have to report or you can find a number of stages by using the Lewis-Sorel method. Please remember, we have done this by applying the method from top to the bottom when the method is applied from the top. So this is how the Lewis-Sorel method is to be used for finding the number of ideal stages in a typical tray conic. So with this, I end my discussion for this particular topic, understanding the method. Now we have understood the method. We have learned how to apply it from the top. In my next video on this particular topic, that is the Lewis-Sorel method, I will be discussing one numerical where I will tell you how to apply the method from the top and get the number of ideal stages, how to get the location of the feed plate, how to get the number of stages in the rectifying section, how to get the number of stages in the stripping section. So that will be done in the next video. For now, thank you for being with me. I hope you have understood the concept. You have understood what steps are to be followed. Again, if you have any doubts, you please mention them in the comment section so that I can solve your doubts. For now, thank you. Thanks for watching. Thank you for being with me. Please subscribe to my channel. Tell your friends to subscribe to it and hit the bell icon so that you'll be notified as soon as I upload a new video on my YouTube channel. The next video will be a numerical that is based on the application of Lewis-Sorel method. So for now, thank you, and I hope you'll be with me in my next video lecture. Thank you. Have a nice day. Bye bye.